Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 17, 2026, just about 6 days ago. It introduces a novel training strategy that combines model distillation with task-specific optimization to produce compact embedding models that rival much larger foundation models. The paper is titled Jina-v5 Text, Task-Targeted Embedding Distillation. And as we'll see later, the performance gains on standard benchmarks are quite significant. Alright, Figure 1 illustrates the system's architecture, which is built around a standard transformer backbone. The standout feature here is the set of task-specific low-rank adaptation adapters shown on the right. Depending on the user's input task, whether it is retrieval, clustering, or text matching, the model dynamically activates the corresponding adapter to specialize the processing. The pipeline wraps up with last token pooling, generating a final embedding vector that supports truncation, as shown by the dimension control at the top. So, having seen the design, Table 1 lists the concrete specifications for the two release models. The top rows present the small and nano variants, which have about 600 million and 200 million base parameters, respectively. Crucially, the lower column lists 4 distinct adapter sets for each model, confirming the multitask strategy. Both versions support extremely long inputs up to 32,000 tokens, thanks to the high rope theta settings shown here. The bottom section identifies the starting points. Qwen3 and Eurobert serve as the multilingual backbones. Well, since Table 1 defined the model's architecture, Figure 2 now maps its actual performance across a wide spectrum of languages. The graphic is organized as a heat map, where each cell corresponds to a specific language code on the MMTEB benchmark. The vertical legend on the right indicates relative success, with green representing the best performance among the tested models. The fact that the grid is predominantly green suggests the distillation process successfully transferred multilingual capabilities, rather than just overfitting to high-resource data. Okay, while the heat map showed language coverage, Table 2 details the specific task scores on the multilingual text embedding benchmark. The table groups models by size, with the massive 4 billion parameter teacher model at the top setting the performance ceiling. In the middle block, the new Jina-v5 text small model achieves an average task score of 67, clearly outperforming competitors like Snowflake and multilingual E5. Finally, the bottom section highlights the nano model, which reaches 65.5, matching or beating several larger models, despite having only 239 million parameters. So, shifting focus from the multilingual results, Table 3 reports performance specifically on the English MTEB benchmark. Just like the previous table, models are grouped by size to ensure fair comparisons. In the middle section, the small Jina model achieves an average of 71.7, surpassing the instructed Qwen model and outpacing baselines like Snowflake. Down in the compact category, the nano model hits 71 flat, remarkably outperforming the Gemma model and rivaling the larger KALM Mini. Alright, having seen the benchmarks, Figure 3 breaks down the training objectives behind them. It tracks retrieval performance over time for 3 loss functions: embedding-based distillation in blue, score-based distillation in orange, and standard info NCE in green. On the left panel, notice how the orange and green lines spike early, indicating fast convergence. In contrast, the blue line starts lower but steadily climbs, eventually overtaking the others. The right panel confirms this trend on the full dataset, where embedding-based distillation clearly achieves the highest final score. Well, shifting from training dynamics to deployment efficiency, Figure 5 demonstrates the robustness of the embeddings when they are truncated to smaller sizes. The horizontal axis tracks the embedding dimension as it is reduced from 1024 down to 32, while the vertical axis reports the benchmark score. Both the small model in purple and the nano model in blue maintain steady performance, even when compressed to 256 dimensions. However, notice the sharp drop-off at the far right. Once dimensions fall below this threshold, the retrieval accuracy declines significantly. Wrapping up, 2 takeaways stand out. Combining embedding distillation with task-specific adapters enables compact models to rival massive ones, and they maintain high performance even when compressed. This suggests high-quality retrieval is becoming accessible even for resource-constrained applications. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.